Today we're going to look at ray diagrams for converging lenses. So we're going to take a look at this problem and take a look at the ray diagrams. There are three rules that we use for ray diagrams. Rule number one is a ray drawn parallel to the principal axis is refracted through the focal point. Rule number two is a ray drawn through the focal point is refracted parallel to the principal axis. And rule number three is a ray drawn to the vertex of a lens passes through unchanged. So before we do a ray diagram, we're going to actually set it up, and we need to introduce some vocabulary here to do that. So the principal axis refers to the horizontal line that passes all the way through this drawing. So that's our principal axis, that's what it's called. Now on the other side of the lens, you'll notice two tick marks. The tick mark closest to the lens is called the focal point, focus or focal point. The second tick mark, which is exactly twice as far away, is called 2F. This point is also called the radius of curvature. Just going to label it 2F for now. Okay, so the reason we have this drawing is that it's exactly to scale. So I've constructed this handout in such a way that each of those tick marks is exactly 2 centimeters apart. And the reason I did that is because that's our focal length. So let's go through the problem and identify the important information. A 1 centimeter tall object, that is the height of our object. So right above the problem here, I'm going to write height, O for object. So the height of our object is 1 centimeter. Is placed 6 centimeters in front of a converging convex lens. So the 6 centimeters is our object distance. So we're going to abbreviate that distance sub-object, DL, is 6 centimeters with a focal length of 2 centimeters. So we've taken care of the focal length with the scale drawing that you see. So in order to do this, you need a ruler or at least a straight edge, but a ruler is really what you would want to use. So the object is 6 centimeters away from our lens. I'm going to start right here at the vertex of the lens, which is in the middle, and I'm going to measure 6 centimeters away. Now I happen to know that 6 centimeters is right at the end of the line. And I'm going to construct an object that's 1 centimeter tall. Now, I'm going to go through the 3 rules for ray diagrams. So rule number 1, a ray drawn parallel to the principal axis. So I'm going to start at the top of my object, and I'm going to draw a line that's exactly parallel using my ruler until I get to the lens line in the center of the lens. Okay, so that's rule number 1. The first part. And the second part is reflected through the focal point. Refracted, excuse me, this is a lens. So it's going to bend from here. Oh, I lost the color. So we have the ray that starts at the top of our object, runs parallel, so we lined it up so that it's parallel with our principal axis, which is this black line in the middle, until we get to the lens line. At the point of that intersection in the middle of the lens line, we line it up with the focal point using a ruler, and then we draw it down through the focal point. So that is rule number 1. A ray drawn parallel is reflected through the focal point. Rule number 2 is a ray drawn through the focal point. So now we're actually going to use the focal point on the left side of the lens. So I'm going to start at the top of the object. I'm going to draw a ray that goes right through the center of that focal point. And from the point of that intersection, we're going to construct a ray parallel to the principal axis, moving to the right. So there we go. I'm just running it so it's lined up with that principal axis. The third rule for lenses is that a ray drawn to the vertex passes through unchanged. So again, starting at the top of the object, so I'm going to draw a ray through the vertex of the mirror, and it's going to pass through unchanged. So I'm going to line it up right where the principal axis meets the lens line. That is the vertex of the mirror. So you'll be doing this with a ruler. It should be a little easier. You can see that if you do this correctly, that all three rays will meet in exactly one spot. So just to recap, we have our object, which we got a description of in the problem. It was 1 centimeter tall, and it was located 6 centimeters to the left of the lens. We did three rules. A ray drawn parallel is reflected through the focal point. A ray drawn through the focal point is refracted parallel, and a ray drawn through the vertex of a lens passes through unchanged. So, as I said, if you do it correctly, they all meet in one point. That is what happened here. So we now have to connect that point with the principal axis. And the way we're going to do that is we will say orange. We'll make the image orange. We're going to connect that point to the principal axis, and that is our image. So our object is the green one on the left. The image is the orange one on the right. So let's take a look at the givens on the right-hand side here. Our focal length was actually given. That was 2 centimeters. The image distance is the distance from the lens line to the image as measured along the principal axis. So get your ruler out and measure that distance. So when I measured that, I got 3 centimeters. The next thing we need is our image height. So the image height is the height of this arrow that's upside down here from the principal axis to the tip. So you need to measure that distance. So take out your ruler and measure that. I did, and I got 1/2 of a centimeter. Now you'll notice that that arrow is upside down. So look at our objects. Was our object upside down? No, that was right side up, which means that when I went from object to image, it was turned upside down. Because it is below the principal axis, I'm going to put a negative sign in front of my height here. So, magnification, and we'll come back to magnification. Now let's classify our image. Was it real or virtual? Well, real means it can be projected onto a screen. Real also means that it's on the opposite side of the lens as the object. So in other words, if it is a real image, it will always appear over here. If it is a virtual image, it will always appear over here. And you can see our image is definitely on the real side of the lens. So is it bigger, smaller, or the same size? So this is asking you to compare the size of the image relative to the object. So is the image bigger than the object, the same size as the object, or smaller? Well, the image is smaller. And the last question was the image right side up or upside down? And this image is upside down, and the word we use for that is inverted. So we've classified the image correctly, and we've completed a ray diagram correctly. What you are always going to want to do is check the ray diagram with the math. And the math is extremely easy. All you need to do is memorize a few equations. The first equation I'm going to ask you to memorize is this. If I do, I die. That's the lens equation. So let's write it out. If I do, I die. So 1 over the focal length equals 1 over the object distance plus 1 over the image distance. So let's go ahead and plug this in. We get 1 over 2 equals 1 over, our object distance was how far our object was from the lens line, and that was 6 centimeters, plus 1 over di. So I have to solve this. Now the easiest way to solve this is going to be in your calculator, and the way that I would recommend you do that is use the inverse button, which is right above the x squared key. So essentially, in order to solve this, I have to do 1/2 minus 1/6, and then I have to take the reciprocal of that. So what I would type in is this. Two to the negative 1 minus 6 to the negative 1, because we want to bring it over. Press enter. After pressing enter, you're immediately going to hit the negative 1 button again, and you're going to see answer to the negative 1 appear. You're going to press enter. And when you do that, you're going to get 3 centimeters. So our image distance is 3 centimeters when we do it mathematically. You can see that that checks completely with that ray diagram. So our image was 3 centimeters away from the principal axis. So that distance that that orange bracket is indicating is our image distance. So let's go ahead and check the other things. The next equation we need to use is the magnification equation. The magnification equation is equal to 2 fractions. They are hi-ho and negative d-do. So the other equation that I'm asking you to memorize is hi-ho, d-do. Hi-ho, negative d-do. So if you can remember if I do, I die, and hi-ho, d-do, I would imagine that ray diagrams should be a pretty easy subject for you to learn. Let's go ahead and plug in the information from the problem. So in this case, I'm going to be looking for my image height. That'll be my variable. Our object height was given. That was the height of the object in the beginning that we drew. Again, the height of our green arrow here. And if you remember, that was 1 centimeter tall. So I'm going to put that over 1. My image distance, we already calculated, that was 3. And our object distance was given in the original problem. That was how far the object was from that lens line, and that was 6 centimeters. So go ahead and cross multiply that. And then solve. Divide both sides by 6. Negative 3 over 6 is, of course, negative 0.5. And as you can see, that's exactly what we got for HI. Now, either one of these fractions is equal to magnification, DI over DO, or HI over HO. In this case, because our object height was 1, we could do our magnification as high over ho, which is negative 0.5 over 1, which of course gives you the negative 1/2. Or we'll say negative 1/2 is a fraction. Or you could have done the other part of the equation, which is negative di over do. So negative 3 over do, which was 6. And you would also have gotten negative 1/2 x. So no matter which method you choose, you get the same magnification. So there you have it. We've looked at the ray diagram, which uses the 3 rules. A ray drawn parallel refracts through the focus. A ray drawn through the focus refracts parallel. And a ray drawn through the vertex of a lens moves through unchanged. And then we verified that with our 2 equations. The lens equation, 1 over focal length equals 1 over object distance plus 1 over image distance, or using the mnemonic device, if I do, I die. And magnification is equal to image height over object height, or magnification is equal to the opposite of image distance over object distance, or hi-ho, negative d-do. So that is how you draw a ray diagram and determine the image distance, the image height, the magnification, as well as classify the image. I hope you enjoyed learning about ray diagrams.